In this video, we will be describing the molecular shapes of molecules that violate the octet rules. So in other words, the central atom is going to be in the third period or greater, and so we have somewhat more complex molecular shapes to consider. If there are 5 electron regions, the optimal structure turns out to be a situation where we have a combination of the shapes that we've already seen. We have a combination of a trigonal planar structure along with a linear structure. And so in this case, it appears as if it is two triangles that are connected at the base of the triangle, and we refer to this as a trigonal bipyramid. The angles in this structure are of two different types. In the equilateral triangle, the angles are 120 degrees, but then in the angle between the axial position and the so-called equatorial positions, the angle is approximately 90 degrees. So, a good example of this would be something like xenon difluoride, where the structure has the two fluorines, and then also has some lone pairs. We have to consider situations where how much space is being occupied by the various kinds of electron pairs. And so it turns out that the equatorial positions actually allow for the greater angles, and therefore makes it easier for the lone pairs to be located in equatorial positions as opposed to the axial positions. The bonding pairs between the xenon and the fluorine are somewhat elongated because they're being shared between two atoms as compared to the lone pairs, which are drawn tightly towards the central atom. And so therefore, generally, the structures that we will consider here, if we have lone pairs, we will preferentially put them into equatorial positions before we have to put them into axial positions. This slide summarizes the possibilities of the various shapes, and it's recommended that you memorize these. So if all 5 of the positions are bonding, as in something like PCl5, then the molecular shape is described as being a trigonal bipyramidal structure. If 4 of the positions are bonding and only 1 of them is the lone pair preferentially goes into the equatorial position, and this produces a structure that we describe as being a seesaw type structure. And so in this case, there are the 2 fluorines of SF4 that are located in equatorial positions, but then the second pair is also located in axial positions. And then the third example is something like chlorine trifluoride, and in this case there are 3 bonding regions and 2 lone pairs. In this case, both of the lone pairs go into the equatorial positions. This is a molecular shape that is described as T-shaped. And then finally we have 2 bonding regions and 3 lone pairs, and this is the example of xenon difluoride. All 3 of the lone pairs go to the equatorial positions, and we describe this being a linear structure. As the final possibility, if we have 6 electron regions, the electron regions will go to the corners of an octahedron where all the angles are 90 degrees. And so in this case, if all of them are bonding, the molecular shape, as in SF6, is described as octahedral. If we have 5 of the bonding regions and 1 lone pair, and in this case this is IF5, is a good example. In this case, we say that we have a square pyramidal molecular shape. And the final example here is 4 of the bonding regions and 2 lone pairs. To get the lone pairs as far away from one another as possible, we put them on opposite sides of the octahedron, and so in this particular case, this molecular shape for something like xenon tetrafluoride is described as being a square planar structure where all of the angles between the fluorine, the xenon, and the fluorine are approximately 90 degrees. At this point, we want to consider the effect that the size of the atom that is attached to the central atom has on the molecular shape and any kind of distortions that can occur. So, in our example of methane, where there were 4 bonding electron regions, the angles were all the optimized tetrahedral angle of 109.5. However, if we don't have all the same atoms, say for example in something like chloromethane, for the 3 regions that involve bonds to the hydrogens, since hydrogen is quite a bit smaller, that bond length, the carbon-hydrogen bond length, is quite a bit smaller than the carbon-chlorine bond length. And so as a result, then, the electrostatic interactions between the hydrogen atoms is slightly greater than the interaction between the hydrogen and the chlorine. And as a result, this causes a distortion so that the HCH angle increases slightly at the expense of the HCCl bond angle. And this then produces a slight distortion, but ends up being a slightly more energetically stable situation for this particular molecule. So, bond lengths can have an effect by the distorting of the structure, and this can also be a result of forming multiple bonds as well. As we had alluded to earlier in terms of the effect of the lone pairs in the trigonal bipyramidal structure, lone pairs tend to take up a little bit more room around a central atom than bonding pairs, and so this can then also be observed when we have molecules such as ammonia or water. Turns out that if we compare the structures of methane to ammonia to water, we are essentially replacing a hydrogen that is attached to the central atom with a lone pair. And so the optimal structure, the tetrahedral structure, is observed in methane. The angle is pretty much the 109.5 degrees. But in the ammonia, since the lone pair takes up a little bit more room than the bonding NH bonds, there is a slight compression of the H and H angles, and this is observed experimentally. In the case of water, that is since there are 2 lone pairs, the angle is compressed even further. And then finally, we want to consider the effect of multiple bonds on any kind of distortions that are observed. So in the example that you see here, we have ethane. The formula for ethane is C2H4. There is a double bond between the 2 carbon atoms. We would expect that there would be 3 electron regions around the carbon atoms, which has a trigonal planar molecular shape with optimal angles of 120 degrees. Turns out that the HCH angles are somewhat compressed in comparison to that because the double bond has multiple electron that are being shared between the two carbon atoms. This takes up more room around each of the carbon atoms than the CH bonding pair of electrons, and therefore compresses the angle slightly. A very similar and isoelectronic molecule is that of formaldehyde. In this case, the double bond between the carbon and the oxygen is the bonding region that takes up slightly more room and compresses the angle between the H, the C, and the H ever so slightly.